The next problem, which is 2-34 of our book, says that one-dimensional steady-state conduction. So as soon as we see the word one-dimensional, therefore that would tell us that T is a one-dimensional heat flow. Means T would either be a function of X or Y or Z if it is a Cartesian coordinate system problem. Steady state condition. So as soon as we see the word steady state condition, so that would mean that dou T by dou T would be 0. With the internal energy generation, so there is Q dot occurs in a plane wall. So we would be dealing with Cartesian coordinate system, and that plane wall has a thickness of 50 millimeters. So this is the plane wall that is shown over here, and this has a thickness of 50 millimeters and a constant thermal conductivity of 5 watts per meter Kelvin. So properties are constant. It means that the material is isotropic. For these conditions, the temperature distribution has the form Tx is A plus Bx plus Cx square. The surface at x equal to 0 has a temperature of 120 degrees Celsius. So the surface at this face is at 120 degrees Celsius, and at this point x is 0. So this problem is a little bit different from the previous one, in that in the previous problem x is equal to 0 was at the mid plane of the wall, whereas in this case it is not. The surface at x equal to 0 has a temperature of 120 degrees Celsius, and it experiences convection with a fluid which is at 20 degrees Celsius. So on this side we have a fluid, the temperature of which is 20 degrees Celsius, T infinity, and H is 500 watts per meter square Kelvin. So when that particular fluid is flowing over this surface which is at 120 degrees Celsius, the convective heat transfer coefficient is then 500 watts per meter square Kelvin. The surface at x is equal to L is well insulated. So the other surface, which is the other face, is well insulated. In part A, it says that applying an overall energy balance to the wall, calculate the internal energy generation rate Q dot. So we have to find out Q dot using overall energy balance. See, we used to find out the internal energy generation rate using the heat diffusion equation. So if someone thinks that why can't we do the same thing again, that why can't we find out this Q dot using the heat diffusion equation in Cartesian coordinate system? See, the reason is, in Cartesian coordinate system we have dou y by dou x of k dou t by dou x. So over here we are given the temperature distribution form, the form of the temperature distribution, but we do not know the values of A, B and C. So in fact what we know is only the form and not the complete equation. So if we derivate it, we will get B plus 2cx, and if we derivate it again we will get C. So we do not know the value of C, so therefore we won't be able to use that heat diffusion equation to find out Q dot. So that is why we are being asked to find out Q dot by applying the overall energy balance to the wall. And then in part B we have to find out the coefficients A, B and C. So in the previous problem we knew the complete equation. In this particular problem we only know the form of the distribution and not the complete equation, because we do not know the constants and the coefficients. So we have to find out the coefficients A, B and C, in fact the two coefficients and one constant, in part B by applying the boundary conditions to the prescribed temperature distribution. So as far as part A is concerned, when we apply the energy balance, first of all kindly take a look at this diagram. There is Q dot, K of this wall is constant, 5 watts per meter Kelvin, and this is the temperature distribution A plus Bx plus Cx square, and we do not know the exact temperature distribution, we only know its form. So starting with the energy balance would be E in plus E generated is E out plus E stored. Now in here you will first try to find out E in, means energy going into this wall, and there are two faces. This is one face and this is the other face, FACE face. So at this particular face or at this particular surface, T naught is 120 and outside fluid is at 20. So heat would be in fact coming out and not going in, and the other surface is well insulated, so there won't be any heat transfer from this surface. So in fact there is no heat which is coming in, therefore E in is 0. In fact it is only E out which exists, and E stored will also be 0 because we were told in the problem that the system is working under steady state conditions, so therefore E stored would be 0, dou T by dou T would be 0. So we will be left with E generated on left hand side of the equation and E out on the right hand side of the equation. Now E generated is Q dot, but this Q dot has got the units of watts per cubic meter, so therefore we need to multiply it by volume. So in the next step we are multiplying it by volume so as to get the dimensions, the units of the left hand side as watts. E out energy is coming out of this wall via convection, because the fluid will convect away energy, and convection expression is HA delta T, so we have written HA delta T. The volume may be written as A times thickness, the surface area of this is the wall having 3 dimensions, so we need to multiply all the 3 lengths. So 2 of the lengths which are on this side, which are on this side, would be area times this L or thickness, and this is the same area through which the convection heat transfer is taking place, so therefore A will get cancelled out, and we will have H times Ts minus T infinity on the right hand side of the equation, and this L or thickness or delta X, whatever you want to call it, will be brought into the denominator. So we know H as 500, we know Ts as 120, and we are given T infinity as 20. The thickness of this wall is 0.050 meters, 50 millimeters. So we get 1 million watts per cubic meter as Q dot. Now in the second part we need to find out the values of A, B and C. So now in order to find out the values of A, B and C, we have to apply the boundary conditions. This is what we were told in part B. Now what are boundary conditions? Boundary conditions means the things that we know. So what do we know in this particular problem? We know several things. For example, the first thing that we know is the temperature at this surface is 120 degrees Celsius, means that at x is equal to 0, temperature is 120 degrees C. So if we apply this particular boundary condition in the temperature distribution expression, A plus Bx plus Cx square, so we are saying that at x equal to 0, so wherever we see an x we will put 0, at x equal to 0 temperature is 120, so the left hand side would be 120, so we get A as 120, and the units of A would be the same as temperature. The units of B however would be degrees Celsius per meter, and units of C would be degrees Celsius per square meter, so that when we multiply C by x square we get the units of T, and when we multiply B by x we get the units of temperature. Now what is the second boundary condition? There are a couple of more things that are going on, and for example, one of the things that we know is that at x is equal to 50 millimeters heat transfer is 0 because it is well insulated. And another thing that we know is that at this face, at x is equal to 0, whatever heat is conducted to this face, whatever heat comes to this face, where it will come from? It will come from the source of energy generation. If this is the source of energy generation, we do not know where it is placed, but it is somewhere in this wall. So wherever is that source, the heat will be conducted to this face and it will be transferred further via convection. So what we can say that is that the energy which will come out, the energy which has reached this face at x equal to 0 will be further transferred via convection. Means Ka dt by dx at x equal to 0 will be equal to Ha delta t, What is Ka dt by dx? It is the energy conducted. And when we say dt by dx at x equal to 0, it means that the energy conducted till this point, till this face, till this surface. The same energy will be further transferred via convection, and this will be true, means that the energy conducted from one point to the other is the same as the energy conducted from second point to the third point. This equality will hold true as long as the system is under steady state conditions. Otherwise this equality will not be true. So areas will get cancelled out, because it is the same area through which conduction is taking place, and that is the same area through which convection is taking place. And we will have K dt by dx at x equal to 0 as h times delta t. So K times dt by dx means b plus 2cx. If we differentiate t, which is a plus bx plus cx square, we will get b plus 2cx, and it will be evaluated at x equal to 0. The right hand side remains the same. Now when we will put x is equal to 0 in b plus 2cx, of course there is no x in b, so therefore 2cx would become 0, and we will be left with kb on left hand side. And h times delta t on the right hand side. So we know all the values except b. We are given k as 5, we are given h as 500, we know t as and t infinity. So we will get b as 1 exponent 4 degrees Celsius per meter. And then in the last, since we have to find out 3 unknowns a, b and c, we must have at least 3 boundary conditions. So we have applied 2 boundary conditions. The third boundary condition is the one that we were discussing a little earlier, that at x equal to 50 millimeters heat transfer is 0. Is 0. So at x equal to L, the heat that will be conducted till x is equal to 50 millimeters will not be further transferred, because it is well insulated. So therefore minus K dt by dx at x equal to L would be 0. So therefore dt by dx at x equal to L will become 0, because 0 upon minus Ka would give us 0. See, over here we are writing minus K dt by dx, and over there we only wrote K dt by dx, because over here it was minus K dt by dx, but then the heat was flowing in the negative direction. Over here it would be minus K dt by dx, and since the heat is flowing in the positive x directions, so therefore minus times plus would remain negative. Okay, now dt by dx will be b plus 2cx at x equal to L. Now x is equal to L means x is equal to 50 millimeters. So if we put x as L over here, we will get b plus 2cl as 0. See, if we had applied this boundary condition before, we would then had to stop at this point, because then there had been 2 unknowns b and c. But since now we have applied the other boundary condition first, and we have found out the value of b, so we can find out the value of c from this point onwards. You can apply any boundary condition at any time, but if you had applied this one first, you would have stopped at this point, call it a particular equation number, and then apply the other boundary condition so as to find out the value of b first. So now c, which is minus b over 2L, will give us the value of c as minus 1 exponent 5 degrees Celsius per square meter. So therefore the temperature distribution will now be A, the value of which is 120, plus bx means plus 1 exponent 4x, plus cx means minus 1 exponent 5x square. Now in part C, it says that consider conditions for which the convection coefficient is halved. So this H is now 250 instead of 500. So if the convection coefficient is halved but the internal energy generation rate remains unchanged, so the heat which is being conducted till this point would be the same as it was before. But now the thing is that H has been reduced. Probably they would have changed the fluid, probably they would have changed the velocity of the fluid, and there are several other ways by which we can vary the value of H, but somehow the H has reduced from 500 to 250. So they are asking to determine the new values of A, B and C. So we have to find out the new values of A, B and C, because the temperature distribution will no longer be having the same values of A, B and C as they had in part B, as they were there in steady state conditions. Because you will now realize that when the convection coefficient is halved, so what will happen is that what will happen to the temperature of the wall? Can you figure out what will happen to the temperature of this wall which is at 120 degrees Celsius? See, it was being maintained at 120 degrees Celsius by the fluid which was taking away the energy. But now if the fluid is taking away less energy, how can we say that? Because H has been reduced to half. So when H is reduced to half, of course the energy that will be convected away, that will be taken away by the fluid now, will be less. So as a result of which this T naught will no longer remain 120, rather it will start increasing. And this is the hint that has been given over here, that recognize that T naught is no longer 120. It will keep on increasing. 121, 122, 130, 140, 150, and then after some time it will again attain a new steady state condition. It will again attain a new steady state condition. We do not know what that temperature would be. In fact, we have to find it out, because that new temperature, that new T naught, which will no longer be 120 but greater than 120, will be the new steady state temperature after the system has again attained equilibrium. After some time, maybe 10 minutes, 20 minutes, maybe 1 hour, we do not know how long will it take, but after a certain duration the system will again come into equilibrium. So we have to find out that new value of T naught. You may call it T naught new, or you may call it T naught dash, whatever you want to call it, because that would be the value of A. So now you have to apply the boundary conditions, the 3 boundary conditions again, because we have to find out the new values of A, B and C. Okay, so again starting with the energy balance. See, E in will still be 0, because heat energy would be going out, because the fluid is at 20. The fluid is at 20 and the temperature of the wall is not decreasing, rather it is increasing beyond 120 degrees Celsius. So therefore energy will still not come in, rather it will keep on going out. And when we say energy stored is 0, it means that we are not talking about that transient phase through which the system is passing through, or the system will pass through until it achieves the new equilibrium state. So we are now talking about the new equilibrium state that the system will achieve. Why? Because that new value of T naught, which would be the same as the value of A, cannot be found out in transient phase. We have to wait till the system achieves the equilibrium state again, and that new value of T naught dash would be the value of A, would be the new value of A. So when we say energy stored is 0, it means that we are not talking about that temporary phase, rather we are talking after the system has attained new steady state after passing through that temporary transient phase. So therefore E generated would be the same as E out. Again E generated would be Q dot times volume, and energy is still going out using via convection, so we would be using HA times Ts minus T infinity. Volume may be written as A times L, and this Ts would now be Ts dash or Ts nu, whatever you like to call it. So Q dot remains the same, so it is 1 exponent 6. The thickness of the wall is still 50 millimeters. H has been reduced to half, so instead of 500 it is now 250. Ts dash is the new unknown, T infinity remains the same as 20. So Ts dash is therefore 220 degrees Celsius. So the system will, the temperature of the wall of the system will keep on increasing from 120 to 121, 122, 130, and it will reach 220, and then over there it will stay at 220 degrees Celsius. So that would be the new steady state system, and that value, as I just said, that would be the same as 120. We will then apply the same two boundary conditions to get the new values of B and C. The next problem is 2-46. It says a steam pipe, means we would be dealing with cylindrical coordinate systems because it is a pipe. So a steam pipe means a pipe that carries steam is wrapped with insulation of inner and outer radii Ri and R0 respectively. So there is a pipe and there is then insulation outside the pipe. The inner radius of that insulation is Ri and outer radius of that insulation is R0. At a particular instant, the temperature distribution in the insulation is known to be of the form C1 log of R over R0 plus C2. Probably some of you might question where is it coming from, or should we take it as granted. For the time being you should take it as given, but in chapter number 3 we would be deriving such forms ourselves, and we would also be finding out the values of those two unknown C1 and C2 by applying boundary conditions. So over here we have to find out whether the conditions are steady state or transient, and how do the heat flux and heat rate vary with radius. So first we have to find out whether the conditions are steady state or transient, and in order to find out we have to find out dT by dT, for which we will be starting with heat diffusion equation in cylindrical coordinate system. Over here you will realize that T is a function of R only, and T is not a function of Z and phi. So therefore heat is coming out in radial direction. So the heat is what will happen is that the steam would be at a higher temperature, suppose 500 degrees Celsius, and therefore the steam will come out radially. The steam will come out radially all along 360 degrees, and while the steam is flowing there is no significant change in the temperature of the steam, and hence the temperature of the pipe, and hence the temperature of insulation. So T is not a function of Z, and circumferentially the temperature is not changing as well, as described in the previous lectures. So therefore the second term and the third terms will get cancelled out. There isn't any internal heat generation because all it says is that it is a steam pipe wrapped in insulation, so there is no information on Q dot. So we will be left with the first term again, as I have been emphasizing again and again, that if you most of the times we would be dealing with the first term only, because t would mostly be the function of r only unless otherwise stated. So it would be 1 over r dava by dava r of kr dava t by dava r as rho c dava t by dava t. So we have to find out dava t by dava t. So this thing would be 1 over r dava by dava r of kr dava t by dava r. So 1 over r remains 1 over r dava by dava r of kr times dava t by dava r. Means we have to differentiate temperature with respect to r. So dava by dava r of t, and what is t? This is t, c1 log of r over r naught plus c2. So we have to differentiate this thing with respect to r. See, the second, there are two terms. One is c1 log of r over r naught, the second term is c2. So there is no r with c2. Therefore the differential of constant with respect to r would be 0. Now it is c1 times log of x. So c1 would remain c1, right? c1 would remain c1. Differential of log x is 1 over x, whatever that x is. So therefore it would be 1 over whatever that x is. X is in fact r over r naught. So we will get 1 over r over r naught. And then we have to differentiate r over r naught with respect to r. So when we differentiate x over 5 with respect to x, we get 1 over, the differential of x is 1, and we get the coefficient of 1 over 5. Therefore differential of r over r naught with respect to r would be 1 over r naught. What will happen now is that r naught will get cancelled out and r will also get cancelled out. So we will be left with 1 over r dava by dava r of k c1, dava by dava r of k c1, and there is no r in here. So if we differentiate it with respect to r, dava by dava r of k c1, we will get 0. So therefore dava t by dava t becomes 0. It means that the system is under steady state conditions. The system is under steady state conditions. Now in part B, we have to find out whether how do the heat flux and heat rate vary with radius. So starting with minus k dt over dr and bringing a over here to make it heat flux, the right hand side would therefore be minus k dt by dr. So we have to differentiate this thing. We can now write this dava as d, because now we know that temperature does not vary with time, it only varies with r. So we can always write that partial differential sign with d. So now we have to differentiate this temperature distribution, and we will differentiate it the same way as we had done on the previous page. So now only r will get cancelled out, r naught will get cancelled out, and we would have minus k times c1 over r, minus k times c1 over r. So therefore heat flux is inversely proportional to radius, to r. It said that how do the heat flux and heat rate. So for heat rate we will not divide the left hand side by area. So we will keep the area over here, and the area would be 2 pi rl, and then we would be differentiating the temperature, the given temperature distribution, in the same manner as we have been differentiating it in this part as well as in the previous part. So it would be c times log of the differential of log of x would be 1 over x, so it would be 1 over r naught, and then differentiating r over r naught with respect to r will give us 1 over r naught. The differential of a constant would be 0. So r naught will get cancelled out and r will also get cancelled out. So we will be having minus k times 2 pi l times c1, minus k times 2 pi l times c1. So therefore there is no r in there. It means that the heat rate is independent of r. Okay, the next problem is 2-49. I am not going into the details because I have already solved a lot of problems in this chapter. However, I will go over it briefly. It says two-dimensional steady state conduction. So it is two-dimensional, means the temperature would be a function of two dimensions. Steady state conductions, so dava T by dava T would be 0, occurs in a hollow cylindrical solid of thermal conductivity 16. It means that properties are constant, properties of the material is constant, it is isotropic material. Outer radius of this pipe is cylinder is 1 meters and overall length is 5 meters, and 2z0 is in fact 5, where the origin of the coordinate system is located at the midpoint of the center line. So if we move along one side of that center point, it would be plus z, and if we move along the other side, it would be minus z, just like we had that thickness of the wall, which was 2L is equal to 40 millimeters in one of the previous problems. The inner surface of the cylinder is insulated, and the temperature distribution within the cylinder, means temperature distribution within the cylinder material, within the thickness of the cylinder, is of the form A plus BR square. First of all, you will see that temperature is a function of R and Z. So it will vary, the temperature will vary radially and along the axis of the pipe, along the axis of the cylinder, and not circumferentially. So this expression would have R in it and it would have Z in it. The expression is A plus BR square plus C log of R plus dZ square. We are given A, B, C and D. It means that we know the complete equation. If we know the complete equation, things are a little bit easier as compared to only knowing the form, and if you are then asked to find out the constants and the coefficient, just like we did it in one of the previous problems. So determine the inner radii of the cylinder, so there shouldn't be a problem. All you have to do is apply the Fourier's law. Obtain an expression for the volumetric rate of heat generation, Q dot. So for that we would be applying the heat diffusion equation in cylindrical coordinate system, but now we would have the first term and the third term. First term was 1 over R dava by dava R of Kr dava T by dava R. We do not have the second term. And then the third term was the same as it was in Cartesian coordinate system, dava by dava Z of K dava T by dava Z, plus Q dot will be there, because we have to find out the expression for volumetric heat generation is equal to rho C dava T by dava T. That would be 0 because we are given the steady state conditions. So you should be able to solve part B as well. In part C it says determine the axial distribution of the heat flux. What is the heat rate at the outer surface? So we have to apply the Fourier's law, minus K, Q is minus K, or Q double dash is minus K dava T by dava R, and then we have to evaluate it at R is equal to R naught, because we have to find out the heat rate at the outer surface. Is it into or out of the cylinder? You will come to know with the sign of the answer. Determine the radial distribution of the heat flux at the end faces. What are the corresponding heat rates? So over here we would be evaluating the heat flux, applying the Fourier's law of heat conduction, minus Ka dava T by dava Z, or heat flux means minus K dava T by dava Z, and once we will evaluate it at Z naught, and then we will evaluate it at minus Z naught, means once we will put Z as plus Z naught, which would be 2.5, and then we will keep Z as minus Z naught, and we will then calculate the answer. And then in the last part we have to verify whether the results are consistent. Of course they would be consistent, so we have to apply the energy balance, which we have applied so many times in the past. E in plus E generated is equal to E out plus E stored. So that would bring us to the end of this chapter number 2.